Dr. Fizz, with the statement of the statistical challenge we are going to work with in this chapter and a nice approximation by Stirling that helps us do the math. Well, the number of ways that we can put N1 particles in energy state 1 and 2 in energy state 2, etc., is given by what we had studied before, capital N factorial divided by the individual factorials of the various numbers in the various states. The total number n is given by the sum of all the little n's, and the total energy of the system, is the number of particles in the first energy level times the first energy, plus the second energy times the number of particles in the second, and so on and so on and so on. Now, we do not like products of factorials, so let's first of all notice that if we have a maximization of omega, we'll have a maximization of the log of omega, since as omega gets larger and larger, the log goes larger and larger also. So let's do that. We have the log of n factorial minus the logs of the individual factorials in the denominator. That looks friendlier, but factorials are still complicated, so we go to Stirling. Stirling's formula shows us a nice approximation for n factorial. Now we're going to use a simplified version of this, and we're going to derive our version, and it falls out of this one that was proposed by Stirling and proven by Stirling. So we go here to notice that if you have the log of n factorial, you're looking at the log of 1 plus the log of 2 plus dot log of n. And since we have this nice relationship, we can think of this as multiplying each of these by 1 to get areas of strips. So you have, see, log of 1 times 1, log of 2 times 1. So each of these strips have a width of 1, and then the height is given by the log. See, here's log of 5 with this height, and then we have a little strip of 1, and we kind of offset that a little bit so that the 5 is in the middle, and we can see that that gets us an approximation for the integral of the log of x. So that's going to be the secret to get our simplification, and we're going to use some neat little derivative tricks here. The derivative of the log is equal to 1 over x, log of x. Derivative of log of x is 1 over x. Derivative of x with respect to x is 1. Now, if you do the product rule with the x and the log of x, look at this little result. Nice little effect. The derivative of the first is 1, so we have the derivative of the first times the second, plus the first times the derivative of the second, which is 1 over x. X over 1 over x, x times 1 over x is going to give you a 1, so you get log of x plus 1. But now here comes the neat little trick. If we have the derivative of this thing, x log of x minus x, we will get the log of x plus 1, but the derivative of x with respect to x is going to give 1 with a negative 1 there. That's going to cancel. So this has to be equal to, you take the derivative, equal to log of x. So when we want the integral of log of x, we can then simply write this down. This x log of x minus x, very, very cute trick. Go from 1 to n. And when we do that, we get at the upper limit n log of n minus n, and at the lower limit 1 log of 1 minus 1. Well, the log of 1 is 0, so we get n log of n minus n plus 1. And since our n's are going to be large, we throw away that 1. And that's going to be the approximation that we use in our analysis, that the log of n factorial is n log n minus n. This comes, by the way, from this Stirling formula, this nice formula by Stirling. If we look at his formula here, we can see that the log of n factorial would be equal to the log of this product here. You would then separate that out by sums of the logs. So you have here log of n to the n. You can pull the n down, n log of n, and that would be plus a log of e to the minus n. Pull down the minus n, log of e. Log of e is going to be 1. And then you could have here with your log of this thing, it's all to the 1/2 power. You pull down to 1/2, and then have the log of 2 plus the log of pi plus the log of n. So when you do that, you can see you're getting what we have, n log of n minus n. That's what we derived. And over here, we're going to throw that away. log of 2, or what's that, small log of pi. N's are going to be really large. You might worry about that log of n over here, but don't worry about that, because when you have the log of a number, it's going to be small compared to the number, and here I'm hitting that log with the n. So n, big number, times log of n is going to be way ahead of just log of n. So we throw that away, and this is our formula, which we derived in our own way with that little strip logic with the area. But I wanted to show you how it comes also from Stirling's more general, result. So let's check it out here with a few numbers. I did that with the calculator here, and we find that if we use 10 for n, and 10 is way too small because we're going to be dealing with lots of particles here in our analysis with particles in a room bouncing around. You get 15, and then if you use the formula, you get 13. And if you try it with 50, then with 50, we get here 148.48 for the log of 50 factorial, and if we do it using our approximation, we get 145.6. So what's the problem that we're going to do? Let's state the problem here, and then we will work at the details in the next section. The problem stated is we want to maximize a log of the number of ways, which is given by this sum of logs as we convert the factorial products to the logs of them. And the constraint is all the particles must add up to capital N, and the energy is a constant. So we want to have these things fixed, and then scramble around the particles and various energy levels to see the most probable way to do it, since that's what nature's going to pick. We'll use the Stirling's approximation for the log of n factorial, and if we do that, we will then get for the log of omega n, big N log big N minus n, and then minus the little guys here, little n's log n minus their n's. And if you look at this, the minus n here will cancel with the minus of all the little n's, because all the little n's are going to add up then, because minus times minus here is going to give you a plus, n1 plus n2 plus n3. So all these here are going to cancel, and we're going to be left with n log n on the big N minus n sub 1 log n sub 1 on the little ones. And that's going to be the result we'll pick up with in our next section.